Okay, in the homework, in one of the questions, okay, in the text of the question, the distances are said to be L1 and L2, but in the parts, I call them R1 and R2. There is a typo in the homework. L1 and R1, L2 and R2, they are equal. So that's how R1 and R2 are supposed to be. Now, any questions about friction or anything else we had done? Yes, there is one.
Frictional force has the motion of the car.
Well, in this one, the friction force is in the direction of the motion of the car.
Is there any, in order to, can it happen that the frictional force will be in the opposite direction?
Sure, for example, if the driver presses the brakes, he wants to stop, then the friction force will be in the opposite direction.
What if it's without the gear, moving in the same direction?
If you are moving in this direction in the car, you see, if you imagine the forces acting on the car, there is a drag force in that direction. Now, if you are moving at constant velocity, in that case, there has to be some other force in this direction. That is the friction force. That is pushing you forward. And the reason why it is in that direction is because of the wheels. The wheels, if you are moving in that direction against some force, like the drag force, the wheels are rotating like this, so they are trying to, although the car is moving in this direction, the bottom of the wheels, which is creating the friction force, they are trying to slide in the opposite direction. So that is why the friction force is in the forward direction. Yes, other questions?
About the electrical source, the electrical source, why do they cut into the
Electrical? So, okay.
How do they cut? Because of the static friction,
It's this one. You see, the saw is kind of, okay, one thing is the friction force, but not only the friction force. So it has these teeth, let's say. It just digs into the metal, the wood, and they just move. Other questions? But of course, for example, you can also cut objects by just, let's say, taking a string. It can be made of iron or these thin string, and just rub them on a wooden surface. Although they will be smooth, you can eventually cut through objects if you move fast enough. That would be due to friction. Yes, other forces, other questions?
Iron or more powerful metals with water. Does the system the same?
Well, I mean, that wouldn't be friction. You see, if you hit this an object with a force in the perpendicular direction, eventually you break it. No, I don't think so.
Yeah, you spoke about lowering the gear. You said when you lower the gear, the number of rotations per unit time increases.
Yes.
So my question is because what I thought was that because in motion, what it tells is that when you raise the gear, let's say you move from gear 1 to probably eventually reach gear 4, the car moves back. When you raise it.
Okay.
So I want to know how, also when you lower the gear, it increases the number of rotations.
Okay. Of the engine.
Of the engine.
If you increase the gear, if you keep the number of rotations of the engine fixed, if you increase the gear, it will increase the number of rotations of the wheel, which will cause you to go faster. Okay, now let's go back to our forces. And this relationship. So this is always true. Whichever kind of forces you have acting on the object, if you can calculate all the forces acting and calculate the total work done on the object, in that case the change in the kinetic energy will be equal to always the total work done on the object. Now we had seen some different forces doing some work. In the case of the spring, we had seen that the work done as you go from point x1 to x2, this was equal to minus 1 over 2 kx2 squared plus 1 over 2 kx1 squared. This was always true, independent of how you go from x1 to x2. We had also seen that constant force, the work done as you go, let's say, from the point R1 to the point R2, this is equal to F scalar product with delta R, which is R2 minus R1. This is equal to F dot R2 minus F dot R1. Again, if you look at these two expressions, the work done depends only on the initial and the final points. If there is a constant force, it is always the difference of two functions, each one depending on the initial, one depending on the final point. And then we say in the friction force, the work done by the friction force as you go from R1 to R2, this is not equal to some function of R2 minus some function of R1. Now we have seen that it also depends on how you go from the initial to the final point. So we have these two kinds of forces in which the work done only depends on the initial and the final point. This is the final, this is the initial point, this is the final, this is the initial point. But in the case of the friction force, it is not like that. It also depends on how we went from point A to point B. Now this allows us to classify forces in two different ways. One is what we call the conservative force, and the other one non-conservative force. Now, conservative forces are basically forces for which work done as you go from R1 to R2 is independent of how you go from R1 to R2. In the case of the non-conservative forces, it is the work done as you go from R1 to R2 depends on how you go from R1 to R2. We had already seen two examples. A constant force is a conservative force. Then we have the spring force, which is a conservative force. Now we had seen the friction force is a non-conservative force. This is just a definition. This is how we define it. Now, of course, now you ask what is conserved, what is not conserved. You see, if we have a conservative force, in this case, the work done as you go from point R1 to point R2, we had already seen that this is equal to some function of R2 plus some function, no, let me just change the notation, plus u of R1. It is just the difference of two functions, one evaluated at the final point, the other one evaluated at the initial point. So these are already two examples we have. Why we put the minus sign? Just convention. Somebody in the history at some point, he just wanted to call this the coefficient of this function evaluated at the final point to be the minus one. Why we call it u? Well, whichever one you want. I mean, if you call it w, you will get confused with the work done. So sometimes it's called u, sometimes it's called v, or if you want, just give it an arbitrary name that you like. And if you compare this one with these expressions, you see that for the spring, u of R2 is equal to 1 over 2 kx2 squared plus some constant. And for the constant force, u of R2 is equal to minus f dot R2, or let me just call it R, plus some constant. Well, that constant we don't know. It's just, again, just convention. You can choose whichever value you want. Because the only thing we know is this difference. And when you take this difference, that constant just cancels in that difference. Well, why we make this definition? Well, you said, let's just assume that we have an object and there is only a conservative force acting on it. The total force, let's just denote it by F. F is conserved. It's a conserved force. Conservative force. So my object is just moving around. So I can talk about the change in its kinetic energy. Now the change in the kinetic energy of an object is always equal to the total work done on the object. This is always true. Well, in this case, there is only one force acting on it, which is a conservative force. So this total work is nothing but the work done by our force F. But being a conservative force, we already said that the definition of a conservative force is that there exists such a function u such that the work done by a conservative force is nothing but the difference of these two values, or the change minus the change in u. You see, the change of an object we define as the final value minus the initial value. So here this is the, if you just take minus out, you get the final value of u minus the initial value of u with an overall minus sign. Now let me write it explicitly. The kinetic energy of the object when it's at the final point, this is, let's say it's v2, minus the kinetic energy of the object at the initial point, let's call the velocity v1. This is the change in the kinetic energy of my object as it moves from the point R1 to the point R2. This should be equal to minus the kinetic energy at the point R2 plus the kinetic energy at the point R1. This is the change. This is the definition of the work done by a conservative force. So I can just play with these expressions a bit. So I can just move this one to the left-hand side and this kinetic energy to the right-hand side. So the kinetic energy times V2 plus U of R2, this should be equal to kinetic energy V1 plus the potential energy at the point R1. So let's just imagine this. We have this object, let's say this one. Initially, or at some point in its trajectory, it has a speed v1, a velocity v1, and it is at the point r1. So let's just imagine we are throwing this up. So at some point, it has velocity v1, potential energy r1, the kinetic energy at the point r1. At some other point, it will be at the point R2, and it will have the velocity v2. Of course, the velocity will be different. So as it's flying over this parabola, it has some velocity here, some different velocity over here. The potential energy at this point is different than the potential energy over here. But what doesn't change is this combination. Kinetic energy plus the potential energy is always the same. Its value at the point v1 is equal to its value at the point v2. As it's moving, it doesn't change. That sum doesn't change. So that basically tells us that kinetic energy plus the potential energy calculated at any point on the trajectory has the same value at any point on the trajectory. So as time goes on, the kinetic energy changes, the potential energy changes, but the sum doesn't change. This is what we call a conserved quantity. So kinetic energy plus the potential energy, which we call the mechanical energy of the system, is conserved. Of course, under which conditions? The total force acting on my system is the conservative force. There is no other force acting on my system. Under these circumstances, if this assumption is true, the total force is just a conservative force, then I can define this U for this conservative force. And when I define the kinetic energy plus the U corresponding to this conservative force, that sum is conserved. This U is what we call the potential energy. Corresponding to F. So if there is a force F, if it's a conservative force, we can always define this function U. And if there is this, once we define this function U, the potential energy, the kinetic energy plus the potential energy is always conserved. Of course, it is conserved if there are no other forces acting on the system. Now, any questions? Now let us see what happens if there are also non-conservative forces. So in that case, the total force, well, there might be some conservative forces acting on the system, like if you have some object on an inclined plane with friction, there is the gravitational force, which is a constant force, hence it is conservative. There's also the friction force, which we have seen that it is a non-conservative force. So the total force can be written as the sum of conservative forces plus non-conservative forces. Now, when we calculate the total work done on the object, well, the conservative forces will do some work. Non-conservative forces will also do some work. So it is the work done by the conservative forces plus the work done by the non-conservative forces. So if you just move your object from point R1 to point R2, the total work as the object moves from R1 to R2 will be Well, if we have conservative forces, there will be a corresponding potential energy. So the work done by the conservative forces we can write as minus U of R2 plus U of R1 plus the work done by non-conservative forces. And again, this work total, the total work done on the object is equal to the change in the kinetic energy of the object. So we see that the change in the kinetic energy of the object is equal to minus the change in the potential energy of the object. Of course, this potential energy corresponds to all the conservative forces acting on my object, plus the work done by the non-conservative forces. So the change in the kinetic energy plus the potential energy will be the work done by the non-conservative forces. So if we have a system in which there are also non-conservative forces, of course, in this case, the mechanical energy of the system will not be constant. It will change during the motion. But that change in the motion is nothing but the work done by the non-conservative forces. So, for example, in this example, okay, initially we have this mass over here. Let's do the example. I have the mass over here. Let's say the coefficient of static friction is μs, the kinetic friction is μk. I release the object from here at rest. Then it slides down and reaches the bottom, and what will be its speed? Now, of course, we can just go ahead and calculate the trajectory and how the position of the object changes as a function of time. We had already calculated the acceleration, and from acceleration we can obtain how long it takes for the object to fall from this point to this bottom point, and then obtain the speed when it reaches the bottom. But using this conservation of the, or non-conservation of the energy, we can calculate the work done over here. The work done on the object, the change in the mechanical energy of the object until it reaches this point. So let's first calculate the potential energy. So is okay, what are the forces acting on my object? There is the weight, there is the normal force, there is the friction force. So is the weight a constant force? It's a conservative force. Friction, is it a conservative force? No. The normal force, does that do any work in this example? The displacement will be horizontal. Along the incline, the normal force is perpendicular. So the normal force is always perpendicular to the displacement, so it doesn't do any work. So we can calculate the mechanical energy, which is the kinetic energy, plus the potential energy due to the weight of the object. Now, what is the potential energy of a constant force? We had already said that it is minus F dot R. So let's just choose this as our z-axis. What is F? In terms of its components? mg, in which direction? Pointing downward at the minus z direction. Well, the position of the object, well, it can have some x component, some y component, some z component. So let's say we have the scalar product of these two vectors written in terms of their components. To calculate the scalar product, you just multiply the corresponding components. Well, the force doesn't have any x, so x component is 0. There is no y component. There is only the z component. Multiply the z component of the force with the z component of that vector, and that gives you mg times z. Well, we said that the potential energy is defined up to a constant. I can add a constant over here, but I'm free to choose that constant, whichever value I like. So I just chose that constant to be 0. This is my origin. Let's say this is my x-axis, the other one is z-axis. So this is the potential energy corresponding to the weight of the object. Now, one thing to keep in mind is that this is valid only if G is constant, because only if the force is constant, this is the potential energy. If the force is changing, we will see that G will be changing depending on your height. This expression will not be valid. Now, what is the mechanical energy? Let's say initial. Let's say this is H. What is the initial mechanical energy?
Initial speed.
No. And we just release it from rest. And it slides down. It slides down a distance, let's say L. Well, the initial...
Is potential energy?
Well, kinetic energy is 0. Initially, it has 0 speed. So it is 1 over 2 m0 squared plus mgh. This is the initial mechanical energy of the system. Now, at this point, when it reaches the bottom of the incline, let's say that its speed is v, just before it hits the ground. What is the mechanical energy? One over 2 mv squared plus mg0. The height is 0. This is equal to 1 over 2 mv squared. Now, if there are no dissipative forces, then the mechanical energy should have been conserved. If it is conserved, these two has to be equal. If mu k is equal to 0, non-conservative forces, they don't do any work. It is 0. So the change in the mechanical energy, which is mgh, 1 over 2 mv squared, this is the final value of the mechanical energy, minus mgh, this should be equal to 0. And hence, v should be square root of 2gh. Now, of course, there will be friction force. So first we have to calculate the friction force. So if mu k is non-zero, that is, there is friction force. So what is the magnitude of the friction force? This is our system. We have this mass m. Well, this is it will be moving downward. This is the direction of the speed. So the friction force in this case is pointing backward. Again, to determine the direction of the friction force, I'm not looking at the motion of the object as a whole. I'm only looking at the surfaces that is creating the friction. Well, this object, I'm assuming that it doesn't change its shape. So the surface, the bottom surface that is touching the incline, is also moving with the same speed as the object as a whole. So the surface, this surface of the object is sliding down the incline. So the friction force will try to stop that. So the friction force is pointing in the opposite direction. That is, the friction force is pointing uphill. There is the normal force, and there is the weight. So if we draw the free body diagram, this is the friction force, this is the normal force, this is the weight. So let us just choose our axis x-axis, y-axis. X-axis is in the direction of the normal force. So the normal force is N in the x direction. The friction force, let's say, is magnitude in the minus y direction. And the weight is mg cosine theta in the minus x plus mg sine theta in the y direction. And the magnitude of the friction force is, in this case, mu k times n. So we have to determine what n is if we want to calculate the normal force, if we want to calculate the friction force. Well, you see, the acceleration of the object in the x direction. What is the acceleration of the object in the x direction? It's not accelerating in the x direction, it's only accelerating in the y direction. So ax, which is fx over m, this should be equal to 0. The total force in the x direction is, we have minus mg cosine theta plus n times 1 over m. This should be equal to 0. So we know the normal force. It's just mg cosine theta. So what about the work done by non-conservative forces? So remember, this is our system. We have this inclined plane. This is our mass. So it just slides down a distance L. And we obtain that the friction force, the magnitude of the friction force is mu k mg cosine theta. The work done by non-conservative forces. Somebody else? Okay, what's the work done by this friction force? No, I mean, we will eventually use it, but we already know the force. We know how much it is displaced. So from these two information, how can you write down the work done by the non-conservative force? You see, what we are aiming at is, we will write the change in the mechanical energy, which we already know that it is 1 over 2 mv squared minus mgh. This we had already calculated. And we will equate this to the work done by non-conservative forces. And from this relation, we will extract what the speed of the object will be when it reaches the bottom. But of course, first of all, we have to express the work done by non-conservative forces in terms of the friction force and the distance covered. Come on, we have a constant force. So the work done by a constant force is somebody else. I always see the same hands. Yes. You had your hand? Okay, what's the work done? What is the definition of the work done by a constant force? F times delta R. If we have a constant force, this is always the work done by that constant force. Now, how do we define this scalar product? Okay, F times L. Well, let's substitute the values, the magnitude of the force is mu k mg cosine theta. The magnitude of delta R is, as your friend said, it's L times cosine of what? Cosine of pi. Because the force is pointing in that direction, the displacement is in this direction, the angle between the two is 180 degrees. 180 degrees is in radians, that's just pi. So this is minus mu k mg L cosine theta. Now we can solve for the speed of the object. Just put it over there, you get 1 over 2 mv squared. This should be equal to mgh plus the work done by non-conservative forces, it is just this minus mu k mg L cosine theta. Well, you see, theta and mu k should be such that the acceleration is very small and it will take a very long time to reach the bottom. Or it can be that theta and mu k are such that it will really go quite fast to the bottom. But whether it takes a very long time or a very short time, when it reaches the bottom, the expression for the speed can always be solved from this equation. We don't need to know how long it takes. It's enough for us to know what is this length. Well, by the way, L times h is nothing but L times sine of that angle, theta. If you want, you can also substitute it over there. Now, any questions on this one? It's from here. You see, for a conservative force, the work done as the object goes from some initial point to the final point is minus the potential energy at the final point plus the potential energy at the initial point. This is how we define it. So we also calculated the work done by a constant force as the object goes from the initial point to the final point, and this is what we obtained. So if you just compare these two, we see that the potential energy for a constant force is minus F times R plus that constant, some constant. Look at this one and this one. This part is a function of the final position only. This part is the function of the final position only. So minus U of R2 should be F dot R2 plus some constant. A constant will always be there because it's eliminated by this difference. We cannot fix that constant.
On the slide, the object lost energy
True.
because of friction force.
The object lost mechanical energy because of the friction force.
So we call the friction force as non-conservative.
True.
Because object.
Well, the definition of a non-conservative force is kind of more general. This is basically the definition. Well, you see, it might be that the conservative forces are such that for a given, if you start from a given point and go to another given point, fixed points, there might be no energy loss. So just comparing those 2 points, you might be tempted to say that it's a conservative force. But a conservative force has to have this property for any 2 points. So if you take any 2 points If you just move your object from the initial point to the final point through any path that you like. If this is satisfied, the work done by the force as you go from some initial point to the final point through an arbitrary path is independent of how you go from the initial to the final point. In that case, that force is a conservative force. If a force doesn't satisfy that, then we call it it's a non-conservative force. And if it's a non-conservative force, we cannot define a potential energy. And if you look at the mechanical energy of a given system, in that case, the mechanical energy might change. It might increase, it might decrease, depending on this non-conservative force and depending on the path that you took.
How is this dependent? What aspects?
For example, we had seen one example, the friction force. Here we had already calculated the work done by the friction force. Our initial point is this point A. Our final point is also this point A. So we just imagine two different paths that start from point A and end at the point A. One of them is the object is just at rest there. It doesn't move. So the friction force doesn't do any work. Another path is you take the object from the point A, move it to the point B, and then bring it back. Initial and final points are same. But the work done will be different. And here, the work done, we had just calculated it to be minus 2 mu k times mgl. So we have these two different paths, and for these two different paths, the work done by the friction force is different. Other questions? Now let's study the projectile motion. Let's just assume that we take an object and we throw it vertically upward. We give it some initial velocity in the upward direction. It goes up, and then it will just fall down. Let's say this is the point A, this is the point B, this is the point C, this is the point D, this is the point E. And let's see how various kinds of energy change. So we have what is the initial kinetic energy at the point A? So at the point A, B, C, D, and E. Well, it has some speed V, V0. It has a mass M. So at the point A, the kinetic energy is 1 over 2m V0 squared, somewhere over here. This is the kinetic energy. With black, I will show the kinetic energy. What about the potential energy? 0. With red, I will show the potential energy. What is the total mechanical energy? Equal to the kinetic energy. I will use orange to show that. At the point B, now we started here, we are going upward at the point B. So is the potential energy the same, smaller than this one, or is it 0? Kinetic energy. Kinetic energy became smaller. So kinetic energy will have some value. What about the potential energy? Is it 0? Is it equal to 1 over 2 mv0 squared or some value in between? Well, the potential energy will be increasing because the height is increasing. Well, it will keep on increasing. So the total potential energy plus the kinetic energy should be conserved, that's the total mechanical energy. So the height of the potential energy plus the height of the kinetic energy should be equal to the mechanical energy. So it will be larger, the potential energy, but not as high as 1 over 2 mv squared. What about the mechanical energy at the point B? It's the same. What about the point C? What's the mechanical energy? 1 over 2 mv squared is always the same. What about the potential energy? At the point B, at the point C, what is the kinetic energy before that? The kinetic energy is 0. What about the potential energy? Remember, the potential energy and the kinetic energy should be always equal to the mechanical energy, which doesn't change. So if the kinetic energy is 0, the potential energy should be maximum 1 over 2 mv squared. Now at the point B, now it's going downward. At the point B, it was going upward, now it is going downward. What's the potential energy? It's the same at B, same at C, same at A, larger, smaller, etc. Same at B, the kinetic energy. Potential energy? Both the potential energy and the kinetic energy, they are the same. They are not even swapped. You see, the potential energy depends only on the height, on the position. The height of the point B and the height of the point D, they are equal. So potential energy at the point B and at the point D, they are equal. The mechanical energy is always conserved, it's always the same. So the potential energy plus the kinetic energy should always be equal to the mechanical energy. But if the potential energies are equal, the kinetic energies should also be equal. Now let's come to the point, another thing, the kinetic energies, although they are the same, it just tells us that the speeds are the same. But nevertheless, their velocities are different. One is going upward, the other one is going downward. So they have different velocities, but nevertheless, they have the same speed. And finally, at the point E, the mechanical energy. What is the mechanical energy? Did it change before it hit the ground? No. What about the kinetic energy at the point E? The same as A, equal to the mechanical energy, and the potential energy is 0. So this is how the kinetic and the potential energies change during the trajectory of my object. You see, if you look at from an energy perspective, you can say that what force does, you see here, the reason why the kinetic energy change was mainly due to the acceleration which was created by the force which is related to the potential energy. So force, in a sense, in this example at least, it just converted potential energy into kinetic energy and then kinetic energy back to potential energy. So here we have a maximum kinetic energy, minimum potential energy. So due to the presence of this force, the kinetic energy was converted into potential energy until we reached the point C when the potential energy was maximum, the kinetic energy was a minimum, and from this point on the forces just converted potential energy back into kinetic energy. So that's, you can say that that's one of the jobs of forces. Forces that just convert one kind of energy into another kind of energy. You see, potential energy only depends on the position of the object, not on the history. So if my object is at this point, I mean, my object could have come to that point, going through all these loops, eventually reaching that point, or it could have just gone from here to the top. It doesn't make any difference. The only thing that the potential energy depends on is the position of the object. So the height will be just the height from your reference point.
So at the points B and D, you assume kinetic energy is bigger than potential energy. It could be reversed, or
Sure, it could have been reversed. I mean, if these points B and D are close to this point, then the potential energy would be very small, the kinetic energy would be very large. On the other hand, if the B and D are very close to the top, in that case, the kinetic energy will be very small, the potential energy will be large. Or at some point in between, they will of course be equal to. So what happens is, as the object is moving upward, you start with a large kinetic energy, small potential energy, and then the kinetic energy becomes smaller as the potential energy increases until the object reaches the top. At the top, it is at rest. The potential energy is maximum, the kinetic energy is zero, and then it starts accelerating downward, which means kinetic energy is increasing, potential energy is decreasing. True.
is it arbitrary, or it's always the ground for
Well, let's see.
gravitational potential?
For a constant force, we said that the potential energy at the point R is F dot R plus some constant. Okay, this is the general definition. So basically, what this constant is, if you just say U of R is equal to 0, this is just your constant. If you just put R is equal to 0, this is just 0. So the potential energy at an arbitrary point is this one. Now, what will be the value of the potential at this R is equal to 0? I don't know. I mean, you can fix it to be 0, or you can choose it to be equal to F dot R0, R0 being some arbitrary, some different vector. So in that case, U of R would be equal to F dot R minus R0. R0 is again just an arbitrary vector. If you choose it this way, the potential at the point R0 will be 0. Now back to your question. We had this example, this trajectory. And most of the time, you would set U is equal to 0 on the ground. Most of the time. It's not obligatory. Well, it's basically, you choose your R0 point, which is again completely arbitrary. You can choose any R0 point. You can choose your R0 point somewhere on the surface. In that case, U on the surface will be 0. But you can as well choose your R0 to be somewhere over here. In that case, the potential energy here, let's say, let me remove this one. An alternative choice would be to put R0 over there. Now, if you put R0 over there, the potential at this point is less than 0. For the gravitational potential energy. Now, this is also sometimes another confusing point. How come an energy be positive or negative? But remember, the potential energy is always defined up to a constant. You can choose that constant to be an arbitrarily large positive number or an arbitrarily large negative number. It's just up to you. Now, whenever we are using the potential energies, doing calculations with potential energies, the potential energy will always come in these differences. And as long as you are talking about the differences of potential energies, that constant will just drop out of the calculation. So, short version of your answer. You don't have to choose the ground as the zero. You can choose somewhere high in the sky to be zero, or you can dig a hole and you can choose the bottom of that hole to be zero. Now, the important thing is this expression that the potential energy, gravitational potential energy is equal to mgh or mgz. This is valid only if the weight of the object is constant, only if g is constant. So if you go high up in the sky at heights at which g is not a constant, then you cannot use this one. Then everything changes. But within that limit, you can call the potential energy to be mgz. Z is the height from an arbitrary point that you choose. It can be the ground, it can be this point, the top point, etc. Z is the height of your object relative to your reference point. Other questions?
When I push an object on the ground, I can calculate the friction force. I can calculate the energy which it's lost because of the friction force. But I think I will generate heat and the object will also heat. So I think that the energy which the object lost is less than which we accepted, which we calculated. We calculated the energy which is lost by using the friction brought by.
In this example?
Yes.
Okay.
It lost energy.
Okay.
It also heat.
Okay.
So I think it didn't lose the energy as we accepted.
True. I mean, that's a conservation of energy. Energy is always conserved. It is never lost. But the important thing is the energy of what? In a sense, energy of the universe. Now let's go back to this example. We said that the mechanical energy of the system has changed. The system meaning of this mass. The mechanical energy of my mass did change by this much. So the energy of my mass is not conserved. So if the total energy is conserved, the question is what happened to the remaining energy? What happened to this energy? The energy lost due to friction. Well, to see what happens, just rub your hands. They get warm. That's what happens to this lost, in quotes, lost energy. It is just converted into other forms of energy. And that is what we call the total energy is the mechanical energy plus the internal energy. This internal energy, well, at least heat is part of this internal energy of my system. And due to this friction force, That's one. What happens is some of the what changes is, okay, the mechanical energy changes, it just means that it is converted into internal energy of the system, the heat. Now, as the object slides down in this inclined plane, what happened was some of the mechanical energy of this mass is converted into heat. This inclined plane and my mass, they heated up. And how much did they heat up? Well, this much. Using this expression for the energy, you can calculate how much the temperature of the object changed with some additional knowledge of the material.
This is change of mechanical energy.
This is the change in the mechanical energy. Kinetic plus the potential energy. So in this sense, the name non-conservative forces is also not a good name. They do not conserve the mechanical energy, but nevertheless the total energy of the universe is always constant. Any last questions before you go for a break? Well, thermal energy is what we call internal energy. Not exactly the same, but part of the internal energy is the thermal energy.
Is sound also an internal energy? Is sound?
Well, it is a combined, depends on what you mean inside. Sound can be both mechanical energy because certain things are moving, and also part of it will be eventually converted into thermal energy. Okay, then last question from me. We said that energy is always conserved. So where did the energy of the universe come from? Okay, you can go for a break.